All right, welcome everybody. So I'm pleased to introduce Bolun, who's visiting us from Columbia, the Department of Earth and Environmental Engineering, but true to the tagline of transcending disciplines. He's coming from a power systems background. We're going to be talking about work related to integration of energy storage in electricity markets. So I won't take too much time, and we'll hand the floor to Bolun.
Yeah. Thank you, Jacob, for the introduction and also the invitation. I'm really glad to be here at Cornell, and actually I will later mention why I'm particularly honored to present my work here. But yeah, I'm from Earth and Environmental Engineering. For those who wonder what it exactly means Earth, I think we are the very unique name here. This actually goes to the root of our department, which we started as a mining school. So before there is even Columbia Engineering, there's the School of Mines. Then we have engineering. Then around 1980-ish, I think people don't like the name mining anymore, so we changed the mining to Earth. There's some endorsement issue. We have to keep this department, right? But that's it. There's actually a significant root in our department is actually energy. So this actually can even think about this as all this energy mining department. So energy is actually our main focus, and that's why I'm here in this department. Okay. So today my talk will about three things. The first, obviously, is the power system, okay, which has been around for more than 100 years, right? It has been ranked by the National Engineering Academy as one of the most significant engineering system, right? And this is a system, of course, now is a foundation to human civilization, right? We need to everything we use electricity. And due to decarbonization, we will be even more dependent on electricity in the future. For transportation, for heating, for cooking. Right? In New York, you have to use if you have a new building in New York, it has to use electric stove. No gas stove. Actually, bad news if you are Chinese. You need to cook. Anyway, next, electricity market. Which kind of the concept of electricity market started around the 1980s, but it's really got implemented in 2000. So before that, electricity, the power system is mostly a monopoly system, right? It's usually controlled by the government. Here in the U.S. a little bit different, but starting in 2000, we introduced the electricity market. Which we also call liberalized power system, is that we created a marketplace for generators and supply to trade. We have a price signal, and actually how the market clears behind the scenes actually a pretty complicated optimization problem related to marginal pricing. I've actually talked about a little bit more. But really the idea is we promote competition and transparency through the pricing, and also facilitate integration of new technology, right? With the market, one thing is for market, one critical concept is non-discriminatory entrance. Everybody can play the market, so that's why my third thing I'm going to talk about is energy storage, right? Which is, it's also not new. Actually, I believe even about 20, 30 years ago, there are batteries, at that time lead-acid battery, are on some island to provide frequency stability. But the idea of, large-scale battery energy storage system really started to being deployed around 2015, accompanying the surge of electric vehicles. So now most of the batteries are lithium-ion batteries, and they are increasingly play a vital role in the power system. Okay. So power system, electricity market, and battery energy storage. So how do they play together with each other? I have a pretty good example here from the California from the California power grid. Let me see if I can close this. Okay. Yeah, from the California example. So a lot of curves, but a few things we want to pay attention. One is this is the net. This is the net demand. Okay, So basically demand minus the renewable, so this is the demand we need to supply through the power system. So basically, if you think about a monopoly, it's power system operator job to make sure we have enough generation to keep the lights on, okay? And on the other hand, we have the market, right? Now here is the market clearing price, at the real-time price. You see the price is roughly correlated, right, with the net demand, right? The higher demand, the higher price. With a little bit caveat, you do see the price, actually the price spike happens here, not here, right? And this is correct. That's because of the ramping rate, right? The here, so if you learned about power engineering, you know, sometimes ramp rate is more a bigger issue than the peak demand, so this is causing, so I just want to know this is correct, right? And then you see if you have our battery, right? So in terms of power system operation, if you want a battery, we do want to make sure the demand is more stable or flat. So you would like to discharge here and charge here, so you're kind of shifting the demand to a flatter curve, right? So that's from power system perspective. Now, if you are a market, if you think about a market, you have a battery, you want to make money, the story actually no different than stock, stock trading, right? You're trading stocks, right? So you want to buy energy when it's cheap and sell it when it's high. In that case, you would like to buy energy here and discharge here. So you just see this actually starting getting a more synergetic with how the demand, how would you operate battery if you want to flatten the demand. And third thing is you have renewables here. So one of the reasons we have this kind of curve, which is also called a duck curve, is we have a lot of renewables, okay? So by charging here and discharging here, we also can, actually, depending right on the actual system condition, but more likely we can also reduce the emission in the power system. Okay, so this is like the perfect, example of the perfect outcome, where market, energy storage, and power system can work in harmony. Together, the battery can make money by arbitraging price difference. It helps the power system to be more stable and reliable, reducing the cost, and also reducing the carbon emission, making it more sustainable. Okay, so this is the ideal outcome. And then every perfect case follows with a but, right? We may not be able to achieve this, and that's why we're doing this research. Okay, actually, let's maybe go back. So basically, incentivized by this, right? And we have a lot of new policies promoting the deployment of the battery, right? And so now this is the newest data from actually just released this summer. California has already reached more than 5 gigawatts of energy storage, utility scale battery. And you see here, actually, most of them, so more than 4 gigawatt are standalone batteries. Standalone co-located, which means they participate directly through the electricity market, has a battery, not has a virtual power plant. Okay, and it seems the capacity is significantly increasing over the past few years. Another thing is once you see has more battery entering the market focus changed, right? So most of the battery now are doing energy arbitrage. Okay, so they are basically buying and selling energy. If you're familiar with this topic, at first battery started doing specialized ancillary services, frequency regulation, reserve, but that's a small market, right? So once you have so many battery in the grid, no question asked, is unsurprisingly, they have to go into the wholesale market and basically arbitraging energy difference, price differences. And also KAISO kind of predicts there are, not predict, but KAISO says now they have more than 50 battery projects on their interconnection queue. Of course, not 100% of this project will get deployed eventually, but the KAISO peak demand is 50 gigawatt. On average day, 20, 30 gigawatts. So you see very much, maybe in 10 years or so, the battery you will see like maybe a certain time since the battery supplies most of the demand in KAISO. Okay, so we have a significant amount of new batteries in California. Okay. And then here comes the research question, right? So how do we manage a power system with high energy storage share? And what makes the problem even more interesting / complicated is the electricity markets, right? So here I have a kind of a quick maybe electricity market, or even economics 101. Is how do you define an efficient market, right? Efficient market by definition is kind of the ideal outcome of capitalism. Is by participating in the market, participants try to maximize their profit, but while at the same time makes the world a better place, right? To increase social welfare. You do this with here we have three criteria. One is the market design reflects the physical characteristic of the participants, right? So here, so this is one thing that's a bit special to power system because we simply have so many physical constraints, right? The generator, transmission line, right? Now batteries. So electricity market has been designed, right? It's the concept was proposed somewhere around the 1980s, right? It's when they designed, they considered transmission and the thermal generators. It didn't consider battery as so much at that time. So if we want to have a efficient market, a good market, right? A market that can reach the ideal outcome of the big picture, the market design needs to reflect the physical characteristic of battery, right? That's the first principle, the market design, right? Second is participants need to basically be smart enough, right? They need to be smart, they need to be sensible, they need to be rational, and profit driven, okay? And this is actually also not very trivial for battery. I will talk about it right now, actually, including Tesla. So Tesla is actually also the big player in this, not in addition to their electric vehicle business. And they're actually using sophisticated algorithm and often AI algorithm to build batteries, right? So this is third criteria, the second. And the third is also a bit special to power system is market needs to be competitive, okay? Of course, every market needs to be competitive to achieve efficient market, but for power system, actually also not so trivial. Simply because the transmission constraint, there are a lot of cases where participants can exercise market power. The power system actually have specialized department to do market monitoring to make sure the market is healthy, nobody is trying to do bad things basically. But we basically have these three criteria that we need to work on, okay, to get a good market to reach this. And actually, for now, we don't have a final answer for any of them. Okay, so this is the research field we're dealing with. Okay. So that's a little background. So why we are talking? So some of the questions, if you're familiar with like other market, the stock market, commodity market, we don't really hear about this very often. But why so special about electricity market, right? This is what I often talk with my students. Is the electricity market is a highly engineered market, right? Simply because it has so many physical constraints, right? The transmission constraints, the generator constraints, right? And also electricity travels at the speed of light. You have instantaneous delivery of electricity, and you must ensure supply-demand balance over an instantaneous delivery system, right? So you can consider, imagine that system will be a very, by the way, also, still, even with storage nowadays, it's still not that convenient to store in battery, right? So this is why the entire concept of electricity market is proposed by academia around 1980. So this is, I believe, one of the first books called Spot Pricing of Electricity. Of course, you don't need to read this one. This is like the first, one of the first study, but then there are better books now, okay? Yeah, but this has been a very interesting problem about how to design electricity market. And back to what I mentioned, this is also why I feel it's very honored actually today to talk about this here in Cornell, because we have also many other very excellent researchers here doing this field. Okay, so yeah. Okay, so then electricity market is a highly engineered market. It's a lot of in power system engineering and operation research concept has been poured into this. But why is problematic for storage in particular? What's the problem with battery here? We can talk about this for one day, for an entire day, why we have so many problems. But to put it simple, electricity market were designed solely based on thermal generators. It didn't consider the characteristic of battery, right? If you're familiar with electricity market, we have a unit commitment, day ahead scheduling, unit commitment, real time, right? We have the cost curve, which kind of based on the heat rate curve. So all these things were based on that we need to schedule generator, we need to optimize their up and down time, we have heat rate curve, etc. So everything is kind of based on the characteristic of thermal generators, right? Of course, then you have marginal locational marginal pricing, which for transmission constraint. But we don't really have. Basically, when people design market, they don't imagine they're 20 years in the future we'll think about putting batteries into the market, right? Then what? So then what's the problem with related batteries? Two. This is not an exhaustive list, but two. One is to manage the storage state of charge economically, and to address unique battery degradation and efficiency characteristic, right? Especially the first one. So I guess everybody nowadays, have an iPhone, right? Or no, not iPhone, have a phone, right? When you take your phone out, right? And, to a field, to a road trip, to hiking, what's the number one thing you care about? Is the state of charge, right? You are afraid of your phone running out of the running out of the charge, right? Now, I was back in China this summer. This is particularly true if you've ever been to China, right? You see in China, every place you go, you need to use your phone, right? And, it's basically your identity card in China, right? So you need to be very careful with your state of charge to make sure your battery get charged. But on the other hand, there are like charging, power station, power banks everywhere. So it's actually becoming critical infrastructure in China to make sure everybody's phone gets charged, right? So the same thing, if you think about the power system, right? California nowadays 20% battery, but and they are seems they are heading towards 50% or even 100%. If you have a power system with so many batteries interconnected, number one concern is, well, where's my charge? How much charge left, right? But still, there's no systematic way for the power system operator to manage state of charge. So basically, until maybe 2 to 3 years ago, there's even no such thing called state of charge parameter in the market dispatch software, right? So you can imagine your power system operator clearing the market operating system. There's nothing called state of charge there. Nowadays, some system operator like California ISO, they are monitoring state of charge, but still their approach in managing state of charge is still quite trivial. So basically, still there's not efficient way for a power system operator to economically manage state of charge, and also to address other characteristics. Okay. So basically, that introduced our first study. So first, let's try to establish a baseline understanding. So let's just give in the current market, right? Battery participating current market. Not really a state of charge. So, but what would happen if we just keep adding batteries? What would happen, right? So here we developed a agent-based, a small scale, a small simple agent-based film breaker in which we try to simulate battery participating in day-ahead and real-time markets. Using a simulation model based on ISO New England, right? So we have the day-ahead market and the real-time market, and the real-time market based on the day-ahead pricing, etc. Right? And one particular innovation here, so why we are the first one of doing this, is really here. It's really trying to simulate a real-time market, because if you look at a study about battery, most of them were basically following the same framework by how people assess thermal generator or transmission lines. It's focusing on day ahead, because for thermal, again, back to the point, because for thermal generators, most of their transaction and most of the revenue happens in day ahead market, right? However, for battery charge and discharge, it's arbitrage price differences. So it's like volatility. It's seeking volatility. So actually, battery for real-time market, battery is actually a very important market, and it's a much more attractive market for battery, right? So it's really important here. So if we want to evaluate battery, we need to focus on the real-time market. But real-time market is not that easy. Actually, I would talk more about simply again, the market was designed for thermal generators. So there's not a very convenient way to dispatch, to incorporate battery into real-time markets. Okay, I'll go into detail later. But basically, we need to simulate battery bidding to generate charge and discharge bid using the price prediction. So that's kind of why we call this a kind of agent model, because battery are also running its own algorithm. Here we have one algorithm, one high. Started from one of my work from my postdoc at MIT, and the idea is it's actually what really matters here is the computation speed. So this is kind of based on the dynamic programming, but we develop a quite high computation efficient way to solve this, so that we can incorporate into simulations, like a full year 24/7 simulation. We do this basically repeat and repeat and repeat. So computation speed is really the key here. But anyway, we figure out a way to do this, to give up a day-ahead to real-time participation simulation. And we have a high-level result here. So we do see that the two markets are different. So actually, first, depending on how battery participate in the market, right? Basically, given the same system, same renewable, same amount of battery, but just the battery are participating differently in the market, battery can affect up to 53% consumer cost and 16% of emission, right? Battery are better. If battery participates in the day-ahead market, they're more effective at reducing carbon emission. Well, if battery participates in real-time market, it's better at reducing cost, right? The intuition being that if your generator gets scheduled in day-ahead, so you have a lot of battery in the day ahead. Actually, the battery will replace the thermal generators. You basically have many thermal generators basically being shut down, right? So cutting their emission for all. Where if you participate in real-time market, those generators are already turned down. You just force the generator to operate at the lowest, at a minimal generation, but not effectively forcing them to shut down, right? So that's the intuition. And here we have basically a Pareto frontier analysis doing Monte Carlo simulation. So basically we randomly have battery to participate in different markets, right? So let's say we have say 5 gigawatt of battery, right? So we have maybe 10% battery participate in real time, 90% day ahead, and we Monte Carlo simulation this. And we ended up all the points, so every simulation ended up giving us a average consumer cost and average emission, right? So then by aggregating.
So why does storage reduce carbon emissions? You're assuming something there about the mix of generation for charging and what you're displacing when you're discharging, because a battery is inefficient.
Exactly. So if you are doing a regular system, actually battery will increase carbon emission because of efficiency. So the only case you're starting to see battery is making a difference in carbon emission is you have a lot of renewables. Here, the renewable capacity is 100% every system demand.
So you're not wasting renewables.
Exactly. That's intuition. So this one actually echoes with some of the prior studies. There are some study before showing battery is increasing carbon emissions. This actually is showing true that if we do not have a lot of wind, battery may reduce cost, but doesn't really change the carbon emission here, right? So now, once you have more renewables, this is medium renewables, it's a lot of renewable, we're starting to see the battery participation forming a frontier, right? So this is low carbon emission, low consumer cost. So this is definitely so the more towards lower left, the better. So you do see here when we have more batteries, first the frontier shifting to this good direction, but also by participating in different markets, Burton ended up giving you kind of different emission versus cost trade-off, right?
What assumption are you making about ownership structure for batteries? Like, in these models, are you assuming that there's a single firm that owns the battery and is strategically the market, or is it dispersed among?
Here we assume they are all so in this simulation, they are price influencer, but when they try to design their bid, they are all consider themselves as a price taker. So basically, we assume all the battery are using the bidding, are using the same bidding strategy. So in that case, actually ownership will be the same, whether they not, because they are not really considering market power, right? So one battery will behave the same as all the other batteries.
I mean, do you suspect that kind of strategic owner-operators will underutilize the capacity if they own a significant enough amount, right, in order to maintain the price differential?
Exactly. So we didn't consider that strategic behavior. It's actually on our to-do list. But yeah, if you in practice they should, if they have a lot of batteries, they would start to exercise that. Yes. But here we are still assuming a honest battery, just consider themselves as a price taker, try not to do anything fancy here, right? So this is kind of just the baseline understanding. Yeah. All right. But this is just a baseline study just to show that market participation is very important. It will give you a significant impact. Of course, the system condition matters, but the market participation or design also matters a lot. So this basically lays a big picture that what we do is important, right? And the idea is if we come up with better market design, we may better shape the curve here, given the same storage capacity, right? So that move on to my next study. So we laid out the background, laid out the questions. So now let's talk about the solutions, right? The first, so basically I'm going to propose talk about 3 studies we did, with each of these 3 perspectives. The first is about market design. So how do we develop new market models? I want to mention this is just one solution. It's not the solution, but this is just one solution that we think and provide a good intuition to the problem. First is how do we improve the market design for storage? This is actually a requirement by the Federal Energy Regulatory Commission that system operators should develop new market models to better reflect storage physical and economic characteristic. Okay, and one angle here we are utilizing is the state of charge. Okay, so if you look at degradation data, so this is real degradation data, we see the degradation rate depends critically on the battery state of charge. Okay, so this is more well known, especially to the battery people. On the other hand, a less commonly aware perspective is economic opportunity cost also depend on state of charge. Okay, this is basically the marginal cost of, let's say, the marginal value for energy stored in the battery, and this is state of charge, right? So basically, the more energy you have, the less valuable they are. And if you think about it, yeah, this is following the intuition of the diminishing value, right? The more you have it, the less valuable they are. It's just that if you think of battery pricing, this is actually exactly the same idea. And of course, the theoretical framework behind this is if you use dynamic programming value to go function, you ended up also getting this thing as well, right? So this offers us a very good observation is both these two depends on the state of charge. So we should start consider a model, a pricing model for state of charge. Basically pricing battery value, battery bid based on state of charge. So this is kind of in collaboration with California ISO that we propose a new bidding curve. It just so traditionally bid curve depends on the power. Okay, so this will be how you, if you bid battery, this will be kind of the traditional one. Depends on the power. This is based on heat rate curve to generators. Now we are saying, okay, we can ask battery to bid based on the state of charge. Given system operator like ISO are already monitoring battery state of charge. So basically, system operator can update battery bids in real time based on their state of charge. Okay. If you want to take a peek inside the model, this is that we can formulate it, incorporate a, we do a piecewise linearization, assign different cost and parameter to different state of charge regions. So here we can even incorporate nonlinear battery models. If you look at the actual battery, right, their discharge rate, charge rate efficiency, degradation cost, they all depend on state of charge, right? So we can figure out a way to do that. But I want to mention one caveat that even if you are dealing with linear model, right? right? Even so, linear model would be constant power rating, constant efficiency, constant cost that we consider linear model. Even you are dealing with linear model, the state of charge dependent baiting still makes a difference because the opportunity cost curve, right? So that's opportunity one. This is the physical, right? So we put this into another. So basically, we pick that Joule paper model again and we simulate battery using different state of charge models. So here, this is our model. This is the benchmark 1 segment. This is what's currently being used. This is 5 segment SOC, 10 segment SOC. And these are the kind of the benchmark, the ideal multi-time period model. And this is for linear battery, so that's what I mean. Linear battery is a constant one, okay? And then this is for nonlinear storage. So first, right, obviously, if you have a nonlinear battery, you are, by doing SOC multi-segment models, better fits the nonlinear model. We have a significant improvement if we go from 1 segment to multi-segment, right? This is obvious, right? We are dealing with a more accurate physical model. But even you are dealing with a linear model, right? So physically there's no difference, but simply because of economics inside, we still have a little bit difference here. Not too much, okay, but still we have some, we make some improvement rather than the first. And this improvement is only due to using a different model, okay? But this is simply just show that by doing a multi-segment SOC beta, we can generate real value to the power system operation. Okay. Yeah, so there goes our first study, is the example of how we design market models. So this is not the final answer, but this is one of the answers we think that we contribute here. So that's the market design. So now let's talk about how do we make participants smarter, right? It's the same story that since market but not designed for battery, it's actually not so trivial for battery to bid into the market, especially real-time markets, right? So if you're familiar with electricity market, we have 2 markets: the day-ahead market, aka unit commitment. It's also the forward market, and the real-time, which also called the spot market. Okay, incorporating battery in day-ahead market is actually not that sophisticated, especially when we're talking about the battery. So 4-hour duration. If you go to long duration ones, it's another story, right? The reason is the unit commitment by itself is a 24-hour optimization. So in this case, you can model the especially the state of charge, efficiency, and evolution constraint. You can model the state constraint here in a 24-hour optimization, and you can solve it. Okay. However, so basically you can directly input your battery parameter here, however, the downside being the battery has less profit. Okay, it's more the volatility is not so high, right? So there are some studies showing battery can make 2 or 3 times more profit in real time rather than day ahead, right? On the other hand, the real-time market has been historically not so attractive to thermal generator, except some specialized peakers. But for battery, they really love to participate in economic. We do have data showing in CAISO. So CAISO, California requires battery to bid both in day-ahead and real-time. It's a requirement. But we do see enough data from CAISO showing that battery are strategically trying to avoid getting clear in day-ahead, so they can arbitrage price volatility in real-time. Okay. But the problem is the real-time market is approximately hourly dispatch, right? Some is single period, some place like CAISO, they do multi-period, but the multi-period only covers around 1 hour duration. So you think about it, you have a 4-hour battery, but you only optimize 1 hour at a time. It's just the window is too small to solve everything through optimization, right? And the battery needs to submit charge, have to submit charge and discharge bits. So this what we call, this is basically a non-truthful market mechanism for batteries. Simply means battery cannot get a good market outcome by simply submitting physical parameter. It's forced battery to act strategically to generate bits. Okay, so this is actually one of the very early paper in this field by Professor Warren Powell from Princeton, showing that yeah, you have the volatile prices, so battery generate 1 bit, another bit. And also mentioned there's also many recent research, actually one from one from here, from Professor Wang Tong's group, showing that this market, current electricity market, may not be a true small market mechanism for storage. Okay. So what do we do, right? So we basically need to design beta curves for battery. Okay. Okay, so this is just one example showing how volatile this price is. So this is new price in New York City over 1 day. Not a particularly special day, just like September 7. I believe I took this because I was making the pre-roll version for some Unreal presentation, and that took the price from yesterday. So this is not anything special. This is kind of a maybe on the little bit worst end of the, but definitely not the worst thing. Okay, you see the price can be very, very volatile, and as you have seen, you are making sequential hourly decisions given such a stochastic price. So that could be an interesting stochastic optimization problem. Okay, so this is what we do. So let's introduce the background. Is we are start directly with a dynamic programming framework that we have battery power, the price. This is the price. This is the charge and discharge power. This is the discharge cost. So this will be the instantaneous outcome from the market. But because, right, we are dealing with a sequential decision-making problem, we have a limited capacity, we have an uncertain future. So this is actually the most important one. We need to model the future value to go, aka the opportunity value of the energy stored in the battery, the SOC value function. Okay, that's actually the most important one, and that's the one we don't know, right? It depends on the future. On the other hand, of course, we have to constrain the power rating, charge, discharge, SOC, energy rating, and this is actually the guy who's making things particularly headache because we have limited storage capacity, right? That's why we need to be very strategic because we can only hold so many energy, right? We have limited storage, okay? If you wonder what this guy looks like, yeah, that's our opportunity value I mentioned before. This is basically, if you think about the derivative of this guy, is diminishing, right? The more you have, the less valuable they are marginally are, right? And this actually, think about the problem. This is actually the due to this. So this is where it, the duality theory connects with dynamic programming. And I taught with this talk in business school. Okay, spoiler alert, our algorithm depends on this. Our learning algorithm depending on this, and many of these economics, they're working on advertisement baiting, internet baiting. They actually have some similar idea, basically using the dual to design the learning of baiting strategy, which is kind of interesting to see the synergy between different areas.
So you're arguing that this marginal value line is the same through time?
No, this time vary.
Okay.
Yeah, so this actually makes things, so here, we depending on the, actually these are the feature with the path, but yeah, technically this guy should have T here.
Okay.
Yeah, so it's time varying, so that actually makes things even more, worse. Yeah, and they actually time vary by a lot, so actually it changes by a lot. Yeah, that's a good question. So it's not a statistical distribution, right? It changes the time vary distribution. So that's why I think about a method that previously used. The most common one, this is the most popular one in industry, is the model predictive control. Is nowadays you use some kind of neural network to generate price predictions, and use it to optimize to calculate this, or using stochastic dynamic programming or reinforcement learning. These are more popular by academics, but more sophisticated in practice. Okay. So what we are proposing is to use a combination of dynamic programming with neural network, and the reason is what we do is we use a offline dynamic programming algorithm to calculate historically optimal value functions, okay, and then directly pass the result to a neural network and use a neural network to learn. So basically, it follows the same theoretical foundation to reinforcement learning, right? Is that you try to learn the value to go function, but here we do it in a supervised manner, taking the advantage that we can, given the past 2 years of price data, we can get the historical optimal value function directly trained. And turns out this approach is very reliable, and by doing this, we kind of decompose physical constraints, right, from the learning process. So we calculate value functions, and we have an unconstrained learning problem, and then after we do this, we predict this guy and introduce constraint back. Okay, and this one gives us a very promising result. It shows that in our result we achieved stably 70% to 90% profit ratio compared to perfect foresight. And we show that this is a perfect prediction, but using neural state price data, we do behave better than reinforced learning or stochastic dynamic programming. And by the way, we only takes a few minutes to train this model over a 2-year data. So it's actually very computation efficient and very promising. This is relatively simple. We now have some more projects to see how we can better, including more features of better neural network to do this. And also we show that we consider different market assumptions and different zones. We can different durations, and we can stably get very reliable profit results. Okay, with this. And the key insight here is we kind of find a way to decompose physical constraints from the learning process. Okay, I was speak with really soon. I say I'm a little tight on time, but we also show that by applying transport learning, basically by only updating the last layer, we can also very quickly to adapt a trained neural network, trained model to another area, right? Of the detail in this paper, but I will try to speed up a little. Lastly, on top of the last work is how do we ensure the market to be competitive, or how do we do market clearing? And here, I need to introduce Tesla, Elon Musk. So this is actually what's really happening, right? This is real data from Queensland, Australia. Australia is the most important market for Tesla. Tesla had this product called Auto Bidder, so this is all real, to big battery into the power grid, design based, and Australia is their real market, right? It's their biggest market. And you see this actual how battery operate in practice. You see this basically like quite chaotic. And you can imagine if you're a power center operator, you saw this, it could give you a lot of big headache. Like how do I predict this guy? How do I monitor this guy? Because it is a power center operator responsibility to make sure a reliable operation into the of the power system, right? So this is a big challenge, and also in California, maybe nowadays also Texas. All right. So we propose a framework to use hybrid learning model to predict battery behavior by so it's a combination with inverse optimization. So we consider a model, a battery model with unknown parameter, especially the cost function. So basically, we know the battery follows more or less this optimization formulation, but we do not know the parameter, the detail inside optimization. So we want to basically train a optimization model based on output, just like how you train a neural network. And in fact, we even figure out a way or to can incorporate a input convex neural network into this. So basically embedding a neural network into an optimization and to use it to be able to try to learn how battery react to prices, right? So it kind of we are trying to predict the agent behavior, right? So it's very similar to how you train a neural network using a quadratic norm to loss function, but instead of training a neural network, we are training an optimization model. So that to another extent, it actually looks like bilevel optimization, right? So this one is unknown. This is the most important part, is we do not know the cost function of the battery, right? In this case, we have two solutions. We can directly incorporate a parametric cost function, quadratic SOC, or we can even do a non-parametric, so by embedding a input convex neural network into this, which I think is a very interesting idea, and it's not my credit, it's actually the proposal from our colleague at the UCSD, right? But anyway, we show this. So basically, we get this real Tesla data. So basically, we train a model to predict how battery charge and discharge based on input price profile. We do show that our model-based learning framework perform much better than pure machine learning framework. And in this case, our quadratic model performs slightly better than generic. So basically, we assume a quadratic cost function performs better than assuming a neural network cost function. And the reason is this guy are using a quadratic-based cost function. So this better fit to their real. But you do see that at least you see how battery behave is very incontinuous, right? Kind of very event-based. So that's why it actually works not so well with machine learning pure neural network model. Okay. You also see, okay, by the way, this is already, I should say it already published. Last time I presented probably in the second round review. But anyway, through this study, we show that, here comes my conclusion, that market design is critically important for battery for cost-efficient decarbonization. Nowadays, if you go to some industry conferences, distributed tech, everybody talks about we are using cutting-edge AI to bait batteries into the market, right? So AI-based algorithm analysis is very important. We are having a true AI agent here, right? And incorporated model information can significantly improve AI efficiency, and computation scalability is very important here to perform the study, right? I mentioned that here that we are seeing that battery basically have this frontier trading off between emission and efficiency. So many of our ongoing work are trying to understand, can we actually ship this one, or how much can we ship this one with our all kinds of market design participation solutions. We are now working on some large-scale AI, real AI agent-based. So the first study I talked, they are exactly simple agent, and they are not using AI. We are now trying to using real AI agent-based storage to do some analysis. Okay. So these are the reference to the full work. They're actually all published earlier this year. You see they're all 2023. So I'm really glad I can talk about this immediately after they are published. More are on my website. And finally, I want to acknowledge my funding agencies and my students and collaborators here. Okay. Thank you. Yeah.
We have, I think, a couple minutes. Any questions? I can start with one. So you mentioned the industry reported capture rate of 70% of theoretically achievable profits for storage. Does that differ by markets? Are some markets easier to predict than others? Or do you have a sense if there's data on that?
Definitely. I think still I cannot say how the profit ratio change, because actually what happens is in a more profitable market, the profit ratio actually lower, simply because the price volatility is too high, right? So I think that's actually the case in Long Island. In our simulation, storage makes the most money in Long Island, because Long Island, because of the transmission constraints, they have price spikes like crazy. They make the most money, but they actually achieve the lowest profit ratio. So that's actually one interest. But it's very much, if you think of a profit ratio, actually the more stable or a better regular pattern the price have, you can achieve actually more stable profit, but it's actually less. So in that case, yeah, so we do see there's a lot of geographical dependency here. Yeah. I also want to be fair that our study focused particularly on real-time price, but I know like Tesla, when I talk to them, a lot of their concern is actually about how to coordinate battery operation across multiple markets, even peak shaving. So industry, of course, they don't focus on this particular problem so much as we do, but we just use that as like a benchmark for us, right? Just to be fair to the fair contribution for fair credit for their efforts, right? Yeah.
Yeah, thank you for your talk. I have a question for learning the utility function of the storage for the last piece of work.
Uh-huh.
Yeah, it's very interesting to find the curve actually match the actual action of the storage. But I'm wondering, are there any insights like the quadratic utility function is used in industry for them to come up with a bidding strategy?
Good point. I think they just this is from their own report, saying they are using some kind of a quadratic model predictive control to do that. And one thing is, if you think of quadratic, it does discourage very high power, charge and discharge power. And if you have an actual battery, right, whenever you have high power, you do run into some issues. You do try to avoid that. I think that's one of the motivation that they use quadratic, right, and also just make the operation more centered, right, not to easily swing to the extremes. I do not have the parameter we learned. This in the paper, but I don't know the parameter. Maybe if you take a look at the actual cost, we have better ideas. But yeah, so the reason, why this guy performs well. Yeah, it's based on their report, they are using the quadratic model here.
All right. Oh yeah, Mike.
So for the nonlinear battery characteristics, how do you actually get those curves? Or do you do some experiments or something?
So the actual one, for this paper, the actual curve here is that the battery people also call it Frankenstein battery data. Is you get one figure from one battery paper, right? So maybe one paper on battery efficiency curve. So these are all based on real. Of course, the real data is continuous, right? So we just discretize them. It's all based on real battery papers, but not from the same paper. So this is kind of a little bit of Frankenstein battery data. But often, if the actual paper is more actually the voltage curve. So we actually normalize it or to power, but some actually shows maybe efficiency. For example, efficiency always has impedance curve. So you see the impedance has this. So the low impedance here, high impedance here, meaning high efficiency here, low efficiency here. These two guys often show up as voltage curves. So, but we just normalize everything, and then the degradation will be actually look something like this. It's even more. So we did some kind of pre-processing here. Is there one question?
Okay. More details on how you incorporate the physical characteristics of storage into a neural network model.
How physical characteristics into a neural network?
Yeah.
Is it about this one or the last one?
The last one.
Yeah, so here we do see these parameters are we assume they are to be unknown, right? And then, or maybe the previous figure. So what we do see is we observe price and action, right? We observe this battery action, and we know what the price the battery has been responding to. We want to learn their decision-making model, and we know, or we assume they are using some kind of this optimization model. It's just we want to basically, it's like state estimation. Or whereas here is we want to estimate the optimization parameter from the observation. Okay, and then the most important one is this guy, is the cost function. So although we write it seems as a very like all-in-one problem, but in practice, these two guys are actually very easy to get because that's just the power. If you look at power, there's an upper-lower limit, right? So we can get this two kind of relatively easily. These two, I believe, also, but I think was some kind of iteration between these two, but the cost function is actually the most non-trivial one to get. So what's the cost? And then, depending on your luck, maybe the guy is using quadratic, these two, or associate these two, but just so we have a way to model even non-parametric cost functions. However, it's not very, we don't have many data, so we only validate on the Tesla data. Yeah.
All right, so let's thank the speaker one more time. And thank you all for coming.
Yeah.